A force is said to do work on a particle when the particle undergoes a displacement in the direction of the force. That is, if the displacement vector has a component that lies along the line of action of the force. So the force F shown to the right in this diagram causes the particle to move along the path from the initial position r to a final position r prime, such that the displacement is dr equals r prime minus r, final position minus initial position. For an infinitesimal displacement, the magnitude of dr approaches ds, the arc length of the differential segment along the path. The infinitesimal work done by the force is denoted du and defined as follows. Du equals F times ds cosine theta. Note that work of a force is a scalar quantity as it has a magnitude but no direction in space. So whereas the force itself acting on the particle does have a direction in space and is definitely a vector quantity, work done by the force is a scalar quantity. It's not acting in any specific direction in space, but it could be positive or negative. So if theta is between 0 and 90 degrees, then the force and displacement component have the same direction, so that the work done is positive, because cosine of an angle between 0 and 90 degrees is a positive value. If theta is between 90 degrees and 180 degrees, these vectors then have opposite directions, and therefore the work done is negative. Also, the work done is exactly 0 if the force is perpendicular to the displacement, or if the force is applied to a fixed point that does not move and thus has no displacement. By definition of the dot product, which we did cover in statics, the equation for du can be expressed as follows, where du, the infinitesimal amount of work done, equals vector F dot vector dr. That's the force vector dotted with the infinitesimal displacement vector. Since work of a force involves the product of force and displacement, typical units of work are joule and foot-pound, where 1 joule uppercase J equals 1 Newton meter. In the most general case, the force acting upon a particle is variable, and the work done by this variable force can be calculated as follows, provided that F and theta can be expressed as a function of position, where u sub 1, 2 equals the integral F cosine theta ds. If the force, F sub c we'll call it, has a constant magnitude and direction, then the work done by this constant force can be calculated as follows, noting that F sub c cosine theta is a constant value, where F sub c cosine theta would be the component of the force in direction of the displacement. So we have u sub 1, 2 equals F sub c cosine theta, taking that constant out of the integral, times integral s1 to s2 ds, which reduces down to u sub 1, 2 equals F sub c cosine theta s2 minus s1. Consider the particle shown that has weight w and moves from position s1 to s2. During its motion, its infinitesimal displacement is dr equals dx I hat plus dy j hat plus dz k hat. Since positive y is defined as upward, as we can see in this coordinate system here, then an expression for the weight vector would equal negative w j hat. Therefore, applying the fundamental formula for work, we have the following, where u sub 1, 2 equals integral f dot dr. That would equal the integral r1 to r2, initial position to final position, of the force, in this case the weight, negative w j hat, dotted with the displacement vector, which equals negative w times y2 minus y1. And therefore u sub 1, 2, the work done by the weight, equals negative w delta y. Consider a particle attached to an elastic spring of spring constant k that undergoes an infinitesimal displacement ds. So here's the particle attached to this spring that is currently stretched. Here is its unstretched position. The spring has a spring constant or stiffness k. This F sub s is the force acting on the particle. So it's acting to the left because the spring is stretched, so it's trying to pull the particle back to the left. And ds here represents the displacement of the particle and also of the spring. So the work done is then du equals the force in the spring F sub s times ds. And from Hooke's law, we know that that spring force equals negative ks. So du equals negative ks ds. Letting S1 be the initial position measured from the neutral, unstretched position of the spring and S2 the final position, then the work done by the spring force is as follows, where we have u sub 1, 2 equals integral S1 to S2 F sub s ds. So performing that integration, we get u sub 1, 2, the work done by the spring force, to be negative 1/2 k S2 squared minus 1/2 k S1 squared. To summarize, the following equations can be used to calculate work done by a force.